Like the common ion effect, you can also add an acid or a base to an equilibrium system, and that can also cause a shift to occur. So the effect of pH on how soluble a salt's going to be is just like a Le Chatelier's principle situation, where in this case, if you add some hydroxide, so if you add something that has a pH of greater than 7, that's going to cause the reaction to shift to the left. If you add an acid to this, again, equilibrium system, that acid is going to react with that hydroxide, removing hydroxide from the reaction system, and it's going to cause the reaction to shift to the right. Okay? So, the pH of the solution, if they give you a problem where they say a solution is added with a pH of 4 or a pH of 8, okay, just think of that as they're either adding hydroxide ions or hydrogen ions. Again, in this case, the addition of an acid will cause the hydroxide ions to be removed, and again, that will cause a shift to the right, which makes FeOH3 more soluble. So therefore, iron 3 hydroxide would be more soluble in an acidic solution than in a basic solution. Because again, in a basic solution, you're adding more hydroxide ions. That's going to cause a shift to the left. Okay? Let's look at some more. This is pretty straightforward. So the addition of a base to the equilibrium, again above, will cause it to shift backwards. The solubility of iron 3 hydroxide decreases. Okay, more complicated scenarios arise when the anion of the salt, so again, here's our salt right here, right? Remember, an insoluble ionic compound is called a salt. Okay, the anion of that salt, which is the acetate ion, is a strong base. Okay, it's the salt of that weak acid. For example, silver acetate sets up the following equilibrium. Okay, and we know that acetic acid is a weak acid, so therefore its conjugate base, which is this, is therefore a stronger conjugate base. If we increase the hydrogen ion concentration, and again, how do you do that? You add some acid, or you have this solution in an acidic solution. Okay, then the hydrogen ions, these H pluses, are going to react with the acetate ions, producing more of that weak acid, the H, C2H3O2. Okay, and again, that's a weak acid with very little dissociation. So therefore, what are you doing? You're removing the acetate ions from the solution. When that happens, what does the reaction do? The reaction is going to shift to the right. Okay, so therefore, again, silver acetate is going to be more soluble when the pH is low, because when the pH is low, that means you have hydrogen ions in there. They're going to react with this to remove it from the solution, causing that reaction to shift to the right. Okay, one final example could be lead to carbonate. Again, we've got that equilibrium system with lead ions and carbonate ions. If you add an acid to that solution, so again, you lower the pH, you add some strong acid to it, again, those hydrogen ions are going to react with the HCO3, which again, theoretically should form H2CO3, but again, we've talked about this a few times this year. Anytime you form H2CO3, that breaks down into just water and carbon dioxide. Either way, you're removing some carbonate ions from the solution. That's going to make PbCO3 more soluble. That's going to cause a shift to the right. Okay, a couple of examples here. In which of the following solutions at the given pH values would you expect iron 3 hydroxide to be the most soluble? So looking at our previous example, iron 3 hydroxide has Fe3 plus and OH minus on the product side. If we're trying to make it the most soluble we can, we want to remove some of the product from that solution so that the reaction will shift to the right to make more. Okay, at a pH of 6.7, that's pretty neutral, which means you're not going to see much of a change there. At a pH of 11.1, that's very basic, which means you've got a lot of hydroxide ions in there. That's going to cause a shift back to the left. A shift to the left, it will happen because, again, you're increasing the amount of hydroxide ions on the product side. That will cause a shift to the left. But a pH of 4.5, which is the correct answer, will cause it to become more soluble because the H plus ions will remove the OH ions from the solution, causing a shift to the right. Okay, and anytime there's a shift to the right, that makes that insoluble salt more soluble. Okay, and our final example here, example 2, says what is the solubility of PbOH2 in a solution of a pH of 9? Again, the only reason they're telling you that, clearly they're telling you that to figure something out. If you know the pH is 9, then therefore the pOH is 5. And if the pOH is 5, then the hydroxide ion concentration is equal to 1 times 10 to the minus 5th. Okay, so think about our solution here. PbOH2 is in equilibrium with Pb2 plus and 2 OH minuses. So if the hydroxide ion concentration is 1 times 10 to the minus 5th, and for every 1 lead you get 2 hydroxides, that means that the lead concentration has to be half that amount. And it doesn't matter if you use scientific notation exactly perfectly, because we know that that's all that we need to do here, I believe. Okay, if that the pH can be used to find the pOH, which can then be used to find the hydroxide ion concentration. Okay, so which means that, oh, we know the pH is 9, then the pOH is 5, and the hydroxide ion concentration is 1 times 10 to the minus 5th. Now, remember, that's 2. Remember, when they say solubility, that's X. So this would be 2 times X, which means we do have to take half of that. So 1 times 10 to the minus 5th divided by 2 equals, and that's what the lead ion concentration would equal, 5 times 10 to the minus 6th. Okay, and so we use that, and that is our X value. That is the molar solubility of PbOH2.